We've got a video here, which is a worked example for, well, in the modeling section. And this is an exponential model. Well, it's sort of mixed in with a linear model as well. So this is about hot drink flask. Let's have a look. A manufacturer claims their flask will keep a hot drink warm for up to 7 hours. In this sense, warm is considered to be 50 degrees Celsius or higher. Assuming a hot drink is made at 85 degrees, and its temperature inside the flask is 50 degrees after exactly 7 hours. So it's hot for 7 hours. Find, first of all, a linear model for the temperature of the drink inside the flask of the form big T, which is the temperature, equals A plus B times little t, which is time. So that's the first bit. Then it goes on to ask for an exponential model. Let's just have a look at that linear model first of all. Well, it's kind of fairly straightforward. The linear model is going to be a straight line. We're going to expect that to actually come down like this. At little t equals 0, the temperature is 85. And at little t equals 7, we've got a temperature of 50. So just a straight line between those. These parameters, of course, this is the intercept, which is the value when t equals 0. And this is the gradient, -5. So that's fairly straightforward, really. Okay, of course, what we've done is we've applied these two boundary conditions. Little t equals 0, big T equals 85, and little t equals 7, big T equals 50, in order to resolve the unknowns, those unknowns being A and B. Right, so the second part of part A says, find an exponential model for the temperature of the drink inside the flask of the form big T equals A e to the power of minus kt. So there's a very familiar sort of a negative exponential model. So this is looking at the graph here. This is a sort of decay model that we get. So it's of that form. Again, now if we apply our boundary conditions, first of all, a little t equals 0 boundary condition, big T equals 85, plug those in there. And of course, the Euler's number term here is going to be 1. T is 0, so this whole thing is 1. So therefore, t is going to be 85. So we know big T is 85 when little t equals 0, time equals 0. And then if we apply this second one in here into our revised equation, the revised equation being t equals 85 e to the power minus kt, we can resolve for k. So just without reading through those steps, you pause and just satisfy yourself that that's going to work out to give us k is equal to 0.076. In these models, k is pretty well always a positive constant, and if we want to make it negative, we put a negative sign in front of it. So when we put this negative sign in front, then that's what really identifies it as being a decay. So we've got this comes down here. Sometimes you see these things asymptoting towards some value. Well, this will do exactly that. It will asymptote to a value, but it's less than 50. So it actually crosses this time axis at this point here. Right, so our full model, now we know A and K is temperature equals 85 e to the power of minus 0.076 times little t. So that is that. Okay. And then he goes on and says, part B, compare the rate of change of the temperature of the drink inside the flask of both models after 3 hours. Well, in order to do this, we basically need, here's B at the bottom. We need the gradient at time equals 3. Well, for the linear model, it's the same all the way through, isn't it? So it's just -5. For the exponential model, we would have to differentiate that function this function here, which is our relationship, and get something like this, exactly like that, in fact. And we then evaluate that at t=3. And that's going to work through to minus 5.14 to 2 decimal places. So, so the linear is predicting minus 5 degrees per hour, and the exponential minus 5.14 degrees per hour. You know, actually quite good, quite close, but I wouldn't say that the linear model has as much merit as the exponential one for this sort of thing. Okay, a user of the Flask suggests that hot drinks are only kept warm for 5 hours. Suggests a reason why the user's experience may not be up to the claims of the manufacturer. Well, yeah, the model predicts that temperature asymptotes to 0, which would not happen unless in freezing conditions. So the model is inaccurate. So that's exactly what this is doing. This is asymptoting, as I say, to something, and that something is actually 0. We would have some constant in there otherwise. And yeah, it's not going to happen. It's actually going to asymptote towards the sort of ambient temperature. You know, so if it's kept in a room, it'll be, you know, 20 degrees Celsius or whatever. Okay, so part D, after how many hours is the temperature predicted to be 75 degrees Celsius? Well, assuming the linear model is what we're talking about, then what we have to do basically is substitute 75 in there and evaluate for T. So we have to do a little bit of solving an Explog equation there, which I'll not go into, but that's going to take us through to T equals this expression here, which is 1.65 hours to 2 decimal places. So that is basically it. So quite a nice, interesting model, but it's a classic exponential decay model, and with a little bit of a twist that we're comparing it to this linear model. So hopefully that has been helpful, and thanks for listening.